Okay, let's talk about a huge, hidden problem in manufacturing. In factories all over the world, millions of dollars are just disappearing. They're lost to tiny defects hidden deep inside these giant rolls of material. You see, once a flaw gets spotted, it can vanish the second that roll is moved or cut, becoming this expensive ghost in the machine. But what if? What if we could give every single defect a permanent address, making it literally impossible to lose?
And that question right there is the million-dollar question for so many industries. It doesn't matter if you're making flexible packaging for food or super advanced battery components. A tiny little flaw that you find at one stage can become completely untraceable by the next, and that leads to massive, costly waste. So, to really get a handle on this, I want you to picture a roll of material that's miles long. An inspection system, a camera, flags a tiny flaw. But how in the world do you find that exact spot again after the roll has been moved, stored for a week, and then rewound? It turns out that's a surprisingly tough challenge, with some seriously expensive consequences.
So where does it all go wrong? Well, it's the traditional methods we've been using for decades. The encoders that measure length, they can drift over thousands of feet and get really inaccurate. And if you rewind the roll, poof, that measurement is just gone. If you slit that big roll into smaller daughter rolls, you've completely lost track of which one has the defect. And don't even get me started on manual tags. They fall off, they get missed. It's just a recipe for disaster.
So how do you fix a problem like this? Well, it turns out you have to completely flip the script. The old methods, they were all focused on measuring along the outside of the material. The new solution looks inside the roll itself, using its very structure to create a permanent map.
And this just lays it out so clearly. You see, traditional linear tracking is kind of like putting a temporary sticky note on the outside. But this new idea, radial referencing, it gives every single point on that web a permanent structural address based on its exact distance from the center core. It's part of the roll itself.
And this right here, this is the core idea, the real breakthrough. Every single layer, every wrap in that roll has a unique radius, a super precise distance from the center. So by mapping a defect to that specific radius, you create a permanent address that survives being rewound, stored, and even cut up into smaller rolls.
Here's a fantastic way to think about it. An odometer in your car tells you how far you've traveled, right? But a GPS coordinate tells you exactly where you are. That is the breakthrough here. We're shifting from a simple distance measurement to a permanent, unchangeable location deep inside the roll itself. Okay, so that's the theory. But how does this clever idea actually play out on a noisy, fast-paced factory floor? Well, the process is actually beautifully simple. You just map it, and then you remove it.
It's so elegant. So in step 1, as the material is winding, the system is basically listening to the inspection cameras. It builds a digital map in real time, tagging every defect with its unique radial coordinate. Then, in step 2, whenever that roll is unwound later on, the system just reads that map and signals the machinery to automatically remove the waste at that exact location. No physical tags, no one running around trying to find a flaw. It's all automated.
But it gets even better. This isn't just about finding one defect. It's about creating a complete history, a perfect family tree for every single inch of material. And this is where the idea becomes incredibly powerful for big operations. So when we talk about true roll genealogy, this is what we're getting at. When a massive mother roll gets slit into several smaller daughter rolls, that digital map is automatically inherited. The system knows exactly which daughter roll contains which defects. Think about what that means. You can trace a customer complaint about a tiny finished product all the way back to the exact spot on the original mother roll. It turns frantic guesswork into a precise, data-driven investigation.
All right, so the tech is cool, we get it. But what about the money? What's the real business payoff here? Because this isn't just clever tech, it has a dramatic and direct financial impact.
Now, you might look at a number like 1 to 3% and think, that's not huge. But in the world of high-volume manufacturing, that is an absolute game changer. By no longer having to scrap an entire roll for just a few isolated defects, companies recover a huge percentage of their material yield. And for these industries, that easily translates into millions of dollars saved every year. And because those savings hit the bottom line so quickly and directly, the payback period is just incredibly fast. Most places find that the system pays for itself just through scrap production and fewer customer claims in only 6 to 18 months.
But it's not just about the material you save. The benefits kind of ripple out across the whole operation. You get happier customers because fewer defective products ever leave the building.
And it means way less downtime for your team that would have been spent hunting for the source of a problem. It's a win-win-win.
So let's just pull back for a second and look at the really big picture here. Because what this technology is doing is, well, it's truly transformative. It's fundamentally changing the nature of the material itself, turning it from just a passive commodity into an active, intelligent asset.
And this quote just nails it. This is the big idea we're talking about. With this radio-based digital map, a simple roll of plastic or paper or foil becomes an intelligent, data-rich asset. It carries its own history, its own quality report, embedded right into its very structure. This is a foundational step toward the truly smart, automated factory of the future. It really makes you think, right? What other passive objects in our world are just waiting to be given a digital identity?